In this lesson, I'll show you how to solve underdamped RLC circuits using differential equations. The question reads, a switch is closed at time is equal to 0. If our resistance is 225 ohms, our inductance is 1.50 henries, our capacitance is 4.75 microfarad, and our voltage source E is 75.4 volts, write an expression for the instantaneous current. Our circuit is shown right here, and we will be modeling our instantaneous current using the following equation. Before we do that, we need to determine which type of RLC circuit this is. And we have a table here to help us out. Depending on our A and omega subscript n value, we can figure out whether it's underdamped, no damping, critical damped, or overdamped. So let's start by finding what A is equal to. According to this formula right here, A squared is equal to R squared over 4 times L squared. So we can find A by substituting our R value, which is 225 ohms, and 1.50 henries into here. Also keep in mind that over here A is squared, so if I square root both sides, I'll end up with simply R, and this becomes a 2, and this becomes 1. So we have A is equal to 225 over 2 times 1.50. Let's go ahead and find out what that is. 225 divided by 3, because 2 times 1.5 is 3, and we end up with 75. And the units for A are in radians per second. Next, we need to find the frequency omega n. Omega n, according to this equation here, is equal to 1 over LC. I'll square root both sides to isolate for omega n. And if I do that, this goes away. And on the right side, if I square root this expression, I end up with 1 over the square root of LC. My inductance, according to our question, is 1.50. So I'll replace L with 1.50 henries, and our capacitance was 4.75 microfarad. We need to convert this into farads before we can substitute it into here. So I have 1 over the square root of 1.50 times 4.75 times 10 to the power of negative 6. That's the correct conversion in farads. Using our calculator, we have 1 over the square root of 1.50 times 4.75 times 10 to the power of negative 6, and we end up with 374.6. 374.6 radians per second. Now let's compare A with omega n. We have 75 is much less than 374.6. So let's take a look at our chart. If A is less than omega n, then we have an underdamped circuit. And because we have an underdamped circuit, we can use this template. According to this template, we need to find omega d, which is the frequency for our sine function. That's not hard to do. We'll use this formula next. We have omega d is equal to the square root, which I'll just raise to the power of half, of omega n to the power of 2. Omega n here is 374.6. 374.6 to the power of 2 minus 75 to the power of 2. Let's use our calculator. We have this number to the power of 2 minus 75 squared. Square rooting this, we end up with 367. Omega d is 367. Now we can substitute these numbers into our formula. Let's go ahead and do that. We have our current I, and I'll use the space available here, is equal to E over omega d times L. We have E at 75.4 over omega d, which was 367 times L, 1.50, and this factor is being multiplied to e to the power of negative a, which is 75 times t, and this is being multiplied to sine of 367 times t. This right here represents the current of the underdamped RLC circuit that we're working with. Let's move on to question 2. In question 2, they want us to repeat question 1, but instead of R being what it was originally, R is equal to 0. So let's see what happens. If we substitute R is equal to 0, we end up with an A value equaling to 0. What about omega n? There's no relationship with the resistance, so that stays the way it is. So let's look at our chart. If A is equal to 0, there's no damping. And for circuits where there's no damping, we use the formula for our current, where I is equal to E over omega n times our inductance, and that's multiplied to sine by its frequency times t. So let's substitute the values that we have. Our E, once again, was 75.4. We have 75.4 over 374.6 times our inductance of 1.50. That's multiplied to sine of 374.6 times t. Multiplying this out on your calculator will give you 134 times sine 374.6 t. That right there represents the instantaneous current for an RLC circuit that has no damping. In our next video, I'll show you how to solve overdamped RLC circuits. We'll see you soon.